So it's my pleasure to introduce the last lecture by Remi. So this morning we're finish wrapping up our lecture series.
Okay, so yesterday I explained the proof of the transcendence result of their paper, from which all the other transcendence results are deduced. And so today what I want to describe is the most concrete transcendence result that they deduce from that. And so it's about rational projective structure that I explained last time. And so we fix, so the setup is the following. We take a rational function of y, and we consider a rational projective structure like I defined last time. So it's a couple of equations. Rational projective structure on P1. The pair of is the pair of equations. So the associated rational projective structure on P1 is the pair of equations and so you have the equation EY, which tells you that the Schwarzian, compute the Schwarzian relative to the derivation d over dz of y plus y prime square r of y is equal to 0, and the equation for the inverse function, which we denote EC, which is that if you compute the Schwarzian compared to d over dy of z plus r of y is equal to 0. Okay, and so the solutions of EC are called the chart of the projective structure. And indeed, if we set y, so I'm going to set all z is equal to CP1 and y, which is CP1 minus the poles of R. And indeed, we said that the solution of EC last time defined the local solution, defined charts on y, okay, which based with transition function are in PSL2 of C. Okay, and the solutions of EY are called the uniformizer of the projective structure. Of the projective structure. So in the case of the J function, okay, J will be a solution of EY, but they are not always uniformizer in the usual sense. Okay, this is just a terminology. So the theorem will describe the algebraic relation between uniformizer of such a projective structure. So the theorem, I'm going to write it here. Casal, Freytag, and Naglu says the following thing, is that assume that the Riccati equation which is du over dy plus yu square plus 1/2 of r of y. So this is the Riccati equation over C of y. Has no solution in C of y out. Okay, this is an equation over C of y, and you assume that there's no algebraic solution for this Riccati equation. So we'll explain what this condition means just after. Okay, but essentially this will be true for most function r of y. Okay. Then, okay, so if you consider f1 of t, fr of t power series that are non-constant. Okay, and GR, a uniformizer, which is well defined at F1 of 0, F1 of 0. Okay, but by this, I mean, so they are formal power series, but at the constant coefficient of them. Okay, so if the transcendence degree, so you compute the transcendence degree of this power series, and then you compose with your uniformizer. Okay, so G prime, G double prime. So you see, I've taken the first power series. I compose with the uniformizer, its first derivative and its second derivative. And I do the same thing for all of them. Okay, so until G second prime of this. So how many functions do I have? Here I have 3 R functions. And here I have R functions. So I have 4 R functions. Okay. So if this is strictly smaller than 3R plus 1, okay, is that because something very special happens? Then there exists H in PSL2 of C and the polynomial, so I not equal to G, and the polynomial non-zero polynomial P such that if you compute Fi of T, this is just Fj of T where you apply the homography H. And you have that the polynomial applied to GR of Fi of T, GR of Fj of T is equal to 0. Okay, so this is completely describing the algebraic relations that are among solutions of, about uniformizer composed with analytic functions. Okay, so in the case where you really start, so remark. So if you really start from the J function, so if so on in other cases, but let me just state for the J function. So if G of T equals GR of T is the usual J function. Okay, so from this conclusion, you can deduce, so the conclusion implies in a few lines, I'm not going to make this lines, using that the J function is SL2 of Z invariant, that actually the homography that you thought that is living in PGL2 of Z is living in the commutator in PSL2 of C of PSL2 of Z. Okay, what the commutator means the set of G in PSL2 of C such that G PSL2 of Z minus 1 intersected with PSL2 of Z has finite index. Okay, so this is, I'm mentioning that because this is exactly the usual form of the Ax-Schaunel theorem for the J function. Okay, you at the end you conclude this.
In the theorem, don't we expect to have a consonance degree form R in general?
So yes.
Yes.
So in general, if you take the F1 FR in generic position, then you assume that the transcendence degree is 4R. But you see that if you take all of them to be rational function, then all of them contribute for 1. Okay, so to get a meaningful theorem, when you apply it for F1, Fr to be rational function, this is the right bound. So let me first comment on this hypothesis about this Riccati equation. And so what is the meaning of this assumption? Meaning of the Riccati equation. And so I will start by re-explaining what I explained last time. So we have Z is equal to CP1 and Y is equal to CP1 minus the poles. And so to a projective structure, we associated the following data. So you have, so P was the invertible jet from, I never know in which direction, from Y to Z, okay, which was projecting on Y, okay, and which was a PSL2 of C, or PGL2, yeah, PSL2 of C, principal bundle. Okay. And we were given a delta, a flat principal connection on P with associated foliation H delta, which is regular. Okay, so this has dimension 1, this has dimension 4, and this foliation is of rank 1. And then we had a third the data is that we can use the isomorphism between P and the other jet space, and then project of Z. So this is PZ and this is PY, and such that this is transverse to the foliation H delta. Okay. And so how do you recover the functions from this foliation? Is that such that if GR is a uniformizer, if you look at the application which to Z maps to Z, GR of Z, GR prime of Z, G double prime R of Z, okay, is take the values, so it's tangent to the foliation H delta. Okay, so if you look at the section of here which are tangent to the foliation, you'll find the uniformizer. And if you look at the section here which are tangent to the foliation, you will get the projective the charts of the projective structure. Okay. So what is the meaning of this Riccati equation is the following proposition, which says that the following are equivalent. That this Riccati equation has no solution in C of Y H, and that the Galois group of this connection delta, which appears here, is equal to PSL2 of C. Okay, in the setting to apply the theorem A, the first theorem that I explained, okay, you need that the Galois group is full. Okay, and so this the condition on the Riccati equation will ensure this thing. Okay, and this is essentially the exercise 1.1, okay, in the exercise sheet. Cool. Exercise 1.1. Okay. And so you see, for example, if you take R of Y to be a constant function, okay, the simplest rational function you can think about, then this Riccati equation always have an algebraic solution. Okay, if you take a constant Riccati equation, it always has an algebraic solution. And so this Galois group is never PSL2 of C. Okay, but in the case of the J function, I wrote last time the function R of Y that is associated here, and you can check that this is satisfied. So let me write the first consequence of this statement. So first consequence, which is the easy part somehow. And describes what happens when R equals 1. So when you take only one power series, so if consonance degree over C of F1, so f of Z, G prime of f of Z, so here f of Z, okay, f of T, is one constant. Second derivative. Okay, so what happens when you take only one power series is that the transcendent degree is always 4. Okay. So why? Because we say that this parameterizes a leaf for H delta. So the Zariski closure of this leaf, okay, will be an invariant subvariety, a delta invariant subvariety of P. Okay. So the Zariski closure will be delta invariant subvariety of P. Okay, but this assumption on the Galois group tells you that the minimal invariant subvarieties tells you that the minimal delta invariant subvariety of P is P. The minimal is P. Okay, and so P, as I mentioned 4, so the Zariski closure is P, and as I mentioned 4. Does that make sense? Okay. So to apply, so to get more information about what happens when you take several solutions, you need to write down a theorem of what happens when you take several projective structures on curves and you take the product. So the setting is the following. So now, a product of projective structure on curves, projective structure. Okay, so I'm going to fix. So let Pi, Yi, Pi be PSL2 of the principal bundle equipped with with principal connection delta I. Okay, for I is equal to 1. Okay, so we can take P to be the product of all of them, and Y to be the product of all of them. Okay, and so I will denote by, so I want to take the same, so this is pi. Pij will be the projection on Pi times Pj. Here the projection will be denoted by Pij. 1i times yj, and here this is pi times pj. Okay, so you can project on all of them. Okay, and delta is the flat principal connection, which is the product of them. Okay, so we take our different projective structure, they can be the same, we make the product. Okay, and so the theorem, which is theorem B, from which we will deduce theorem C, will say the following thing. So you need to assume that the Galois group of delta I is always PSL2 of C. Okay. And now you take, let V be an algebraic variety closed algebraic subvariety of V, and L, the leaf of delta. Okay, so this is a R-dimensional foliation, and V, an irreducible component of V intersected with L. Okay, and so you assume the following thing. You assume, which is essentially the content of the previous inequality, is that the dimension of the intersection is bigger than what you expect. So the dimension of V is smaller than the dimension of the intersection plus 3R. Okay. You assume that V, so this is cheap, is the Zariski closure of V intersected with L of V, the component you started with. And you assume that V projects surjectively PRV of V bar in PI. Okay, and this third condition will be automatic, essentially in our case, because of this. Then, okay, so it's equivalent to say that V projects generically on Y, yi, all I. Between 1 and 2? Yes. So that's we assume that somehow, so we assume that we are in this situation. Okay, so there's no relation between the dimension. So this tells you that dimension of V is greater than dimension of curly V.
Yes, but if you compare with 1, maybe it's the wrong.
So this tells you that dimension of V is greater or equal than dimension of curly V. But it's still somehow not that, I mean, it's not that big. Yeah. Okay, so then you have two consequences for that. And the first one is that there exists I different from J, and a delta I times delta J special curve of yi times yj, such that if I project, so V lives here, to project it here, I take the composition. So it's such that pi I times pi j of PRIJ of V is included in Xij. Okay, and this Xij will project dominantly on yi and yj. Did I write here? Yeah, so here I should say projecting dominantly on yi and y2. And the second part is that we can be a little bit more precise, is that if I look at the projection of V in Pi times Pj, and so you see Pi of V lives in Pi times Pj, but it's project on Xij. Okay, so it lives in the restriction of Pi times Pj to Xij. I times Pj restrict Xij. Okay, is the graph of an isomorphism so between two things on Xij, you have the projection. So let's denote by between Li of Pi delta I and Lj of Pj delta j. So there's many projections. So I need to, so where Li is a projection from Xij to Yi, and Lj is a projection of Xyj to Yj. Okay, so here you have this principal bundle Pi delta I. This is generically finite. Okay, this is, so you can pull it back to a principal bundle on Xij everywhere where it's smooth, essentially. Same thing for here. Okay, and actually the PR of JV bar is the graph of an isomorphism. Okay, so you know what V looks like here, and you know what the projection of V looks like here, and even what the projection of V looks like here. Okay. So let me give you the ingredient of the proof. But essentially, this follows from the theorem I explained last time and the Cauchy-Goursat lemma that was explained in the first lecture. And so there's several things I want to explain. And so the first observation is that the fact that we know how to compute the Galois group of the delta I give me what is the Galois group of delta. The Galois group of delta is PSL2 of C to the power R. Okay, a leaf of delta will be a product of leaves of the L1 times LR, and all these leaves are Zariski-dense in the projection, and so the product of the leaves is Zariski-dense in P1 times PR, which is P. Okay, and so this is the sparse group. And so if I use the theorem A plus the property 1, I can deduce that if I project V in Y times Y1 times YR is delta 1 times delta R. Okay, so let's denote these things by X. So X is the projection like that on the Zariski closure is delta 1 times delta R special subvariate. So I'll denote by H the Galois group of the restriction of delta to X. And so H is a proper subgroup of PSL2 of C to the power R. And if you remember, Cauchy-Goursat lemma was exactly describing the proper subgroup of products of simple groups. Okay, but what I need to know is the observation 2. To apply this lemma is that I want to know that H projects surjectively on each GI, on each gal delta I, which is always PSL2. And you see, it comes from my assumption 3. Okay, this is because of 3. Okay, and so now I have a subgroup. So but now I can apply Cauchy-Gousse lemma. Okay, it tells us that there exists. So here I formulated it for groups that were simple up to their center, essentially. So here they are really simple groups. So it tells me that there exists I not equal to j. So let's assume I is equal to 1, g is equal to 2 to simplify the notation, such that, and an isomorphism phi from G1, which is so from gal of delta 1 to gal of delta 2, sigma, such that my group H is contained in the graph of sigma times the other group. Okay. So you have G1 times G2. They are both isomorphic to PSL2. Okay, you have an isomorphism between them. And the graph of this isomorphism is also both isomorphic to G1 and G2. And so the subgroup is contained in something like that. But now if you, because we know what the Galois group of X looks like, we can say how do I write it? Okay. So observation 3 is that if I look now at Pij of X ij is a special subvariety delta G special subvariety of yi times yj, such that the Galois group of delta E times, so let me repeat Xij. This is X, Xij is a projection of X and take the Zariski closure, is included in the graph of sigma. Okay, so this is a general lemma, exercise 2.2. The exercise sheet that tell you that if you have, which describe essentially how the delta special subvariety look like for product, but if you have a delta special subvariety such that the projection of on one factor is already a proper subgroup, then the projection of this variety will be a special variety of the projection for this special subgroup. And so this proves, and so now you can see that this is a curve. This is a, so because yi and yj are curves, so because yi, yj are curves, so yi times yj has dimension 2. So this would be either a point or a curve. Okay, but you know that, and PRI of V. So if you take okay PRI and PI times PRI of V is equal to YI, because V, if you start from the beginning, the assumption 3 tells you in particular that V will project dominantly on yi, because pi project dominantly on yi, we assume something stronger. We assume that V projects subjectively, generically on pi, and so in particular on yi. Okay, so Xij at the end of the day, we first project V here, and then we project V here. Okay, and so the fact that V projects generically in yi will tell you that Xij generically on yi and yj. Okay, and you have no choice because they are curves. This is where I use strongly that they are curves. Okay, and so xij is really a correspondence between yi and yj. And if you don't assume that things are one-dimensional, you need an assumption to get rid, to show that here it's a correspondence. Okay, and for the second case, I'm not going to say much. For the second case, for the second part, okay, and just so the second part is easy. For the second part B, the main observation is that okay, if I look at Prij of V, I can take the Zariski closure. This is delta E times delta G. This is the Zariski closure of a leaf of delta E times delta G, delta J restrict to Xi. Okay, and by definition, this is a minimal delta invariant subvariety, and so this is implies this is a G sigma. So this is implies that Prij of V bar is a G sigma principal bundle over Xij. Okay, so G sigma is isomorphic to PSL2. Okay, and so in particular, this has dimension 4. Okay. So now I want to explain how to deduce the theorem C. So there's several things to do which are straightforward consequence of that, and there's something that is a bit harder. I mean, that at least they use another technique to conclude the proof at the end. And so beginning of the proof of theorem C. Okay, so you start with power series, G1 of T, F1 of T, Fr of T, which are non-constant. Okay, and now I do like I did in the first case. I look at the map from, so I look at the map which goes from CR0 to P to the power R. Okay, and which changes T1 TR, okay, to F1 of T1, JR of F1 of T1. Okay, then you take the derivatives, the second derivative. This lives in the first copy of C, and you do this for TI, 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 TI. And 1 less equal to I less equal to R. Okay, so this is a parametrization. This is a parametrization of a leaf L of this delta, which is the product of the delta. So you see here the T1 TR are different. Okay, in the proof of the theorem, the T1 TR are the same in the statement of the theorem. So now I'm going to do that. Okay. I'm going to look at let V. V is a Zariski closure of the image of the map, which is T. So let me give a name to this. So I will not. This is key. Okay, where I put T, I'm associating T, but with only T. The same. So now You see that by definition, if I compute dim of V, okay, if I assume that the transcendence degree is less than what was expected, less than 3r plus 1, the transcendence by assumption of the theorem we are assuming that dim of V is strictly less than 1 plus 3r. Okay, but this is less or equal than dim of the intersection plus 3r, because we have constructed V to be the intersection of a curve inside the leaf with to contain a curve inside the leaf. Okay, so you see that the first assumption here is satisfied. Okay, the second is not very hard to get. And the third one, you see that this is the theorem that I said before. What is PRE of V? PRE of V, it contains F1 of T, F1 of T, GR of F1 of T, and G second R of F of T. And we said that this is always a Zariski. And 1 and 3 is satisfied by the easy case. Okay. And so the theorem applies. Theorem B applies. And we obtain the following information. Let me erase this. And we obtain that there exists I not equal to j and a polynomial p in C of x1, x2, such that p, and so this is the projection of yi, the projection of yi gives me the gr, so that p of gr of f1 of t f2 of t, so p of gr of f1 of t, gr of f2 of t is equal to 0. Okay, so this is the part A. And what is the part B telling me? The part B is telling me at least that, so I say that V is the graph of an isomorphism between these two things. And the only information I will get, and maybe this is where the proof can be a bit improved, is that these two have dimension 4. Okay, so the only thing that we will get is that the transcendence degree over C of Fi of t, Fg, so Fi of, let me, Fi of t, Gr of Fi of t until the second derivative, and Fj of t until Gr second of Fg of t is equal to 4. Okay, so you see that we are in the case R equal to 4 here. Okay, and these things tells us that something happens if dim of V is strictly less than 7. Okay, in dimension when R is equal to 2. Tells me that if dim of V is strictly less than 7, then dim of V is equal to 4. Okay. So now if I gather, I see that, so there's an algebraic relation between GR of F1 of t, Fi of t, and GR of Fj of t. Okay, so here, this counts for 3 transcendence degrees. Okay, but you see that all the parts which start with GR of Fg of t, this lives in the algebraic closure of these numbers because there is a polynomial between them. And so you can express all the derivative of this one in terms of the derivative of the second one. Okay, so this counts for 0 in the transcendence degree. Okay, now I have 2 power series, this one and this one. Okay, this counts for 1. Okay, so from this I can conclude that Fj of t in the algebraic closure of fi of t, gr of fi of t, gr double prime of fi of t. Okay, this is just by computing transcendence degrees. But you see that I haven't computed what this algebraic relation is. Okay, and what theorem is saying. So the last part of the theorem to prove is that fi, so this algebraic relation is actually fg of t is equal to h times fi of t for some homography h. Okay, I've computed the transcendence degree. Okay, I see that there is an algebraic relation, but there's one that I haven't described here. So how long do I have? Okay, I have 15 minutes. Okay, and so this is where they use methods purely from differential algebra to be able to compute this last algebraic relation. But you see that I've only used that I know that the dimension of V is 4, and actually we know more about V. We know that this is a graph of an isomorphism. But here I've only used that the dimension is 4, and I only get this conclusion. I would like to get this conclusion. And so they use another method. Is that they will work in a differentially closed field. Anyway. And so differentially closed field, they are the analog of algebraically closed field, but for differential equation. So a differentially closed field is a differential field. Let's say, so we denote it U delta because U, we want to remember that this is not an object we have any control on. So we call it U like universe, such that every system of differential equations which have a solution in some extension of U has already a solution in U. Okay, so they exist by general nonsense, but let me give you a construction, an explicit construction of certain object to show you how an explicit construction to show you a little bit what kind of object this is. And so if you start with a K delta, a differential field, you can produce a differential field K star in the following form. What you take is that you take the field of Poisson series over K, and you take the derivation delta star, where delta star is a unique extension, continuous extension of delta. Okay. Satisfying that you send delta star of T. Okay, this is a classical object. Okay, so how do you construct a differentially closed field? You start with K. Okay, and you set K1, which is K0 star. And then you continue. You say K2, which is K1 star. Okay. And if you do that infinitely many times, if you look at the union of the Kn, this will be a differentially closed field. Okay. So these are differential fields that are huge. And so we can do the following. If I give you E, a differential equation, you can associate to it a set of solutions of E in this differentially closed field. Okay, exactly like when you have an algebraic variety, you can take its points in an algebraically closed field, take a differential equation, you take its solution, and its set of solutions characterize the differential equation. It's like there's a Null-Shell for differentially closed field. And so what is the point here? Is that, and by a definable set, we mean a Boolean combination of sets of the form S of E. Okay. And so the point is that we can intersect things that have different nature. We can intersect solution set of autonomous equations with solution sets of equations that are not autonomous, okay, and with algebraic varieties. Okay. And so here is the point of view on this object, which is what are the curves in this setting, in this differentially closed field? So definition. We say that E is strongly minimal. So if it's a curve in this setting, and we mean by that is that every definable subset of S of E is either finite or cofinite. Okay, we don't distinguish between something that is closed and something that is open. So we say that if you take a definable subset, okay, so a Boolean combination of other things, and you intersect with this differential equation, you only with the solution set of this differential equation, you only take something which is finite or cofinite. Okay, and if E1 and E2 are strongly minimal, we say that they are orthogonal. They are non-orthogonal. Let me define the non-matrix. If there exists a definable correspondence between them, so you take D included in S of E1 times S of E2, such that so P restricted to D, Pi restricted to D from D to Si is surjective. Okay, and all but finitely many fibers are finite. Okay, so you only have maybe a finite number of fibers that are not finite. Okay, so if you look at algebraic solutions instead of differential equation, you look at solutions of polynomial equation from this perspective. The only strongly minimal sets are curves, and any two curves are non-orthogonal. Okay, so this is a too-weak notion to study algebraic geometry. But about differential equations, actually, there are solutions of arbitrary high order. There are differential equations of arbitrarily high order that satisfy this property. And there are many which are pairwise orthogonal. So if you look at this relation for solutions of polynomial equations, you don't get anything interesting. But for differential equation, this is meaningful. And so what they prove here to understand this algebraic relation is this corollary of the theorem B, is that if you look for every A inside your differential field, if you look at this equation, the equation that we were looking at, but instead of looking at equal to 0, you look at equal to A. Okay. And for every A, this is strongly minimum. And this follows from the description of theorem B. And the second point is that if A is not equal to B, so let me equation EA, then actually the equation that you get are orthogonal. Okay, so there's no correspondence between the solution of these two equations. And so when you prove that, it's easy to conclude the proof. I'm just going to conclude the proof using that. Is that if you look at, so if you set, so end of the proof. If you take G1 of t, which is GR composed with, so GI of t, composed with your function fi, okay, and the same thing for, okay, JJ, it's not a good, so J1 and J2. J1, J2. And by the Schwarzian chain rule, okay, you can see that J1 satisfies E of G1, so satisfies the equation E1, which is that the Schwarzian of Y plus Y prime square R of Y, this time is not equal to 0, but is equal to the Schwarzian of F1 of t. Okay, the function GR satisfies equal to 0. With the Schwarzian chain rule, you can check that this one satisfies equal to S of F1 of t. And similarly for E2. So F2 satisfies this differential equation. But you see that the polynomial P that we have found, so now if I'm intersecting so in U, in my differential field, if I'm intersecting the solution of E1 times the solution of E2 with the algebraic variety defined by the polynomial P, okay, there's a polynomial P such that there's an algebraic relation between two. This is a definable correspondence between S of E1 and S of E2. And so we conclude that E1 is non-orthogonal to E2. Okay, and actually they are orthogonal when they are equal, so we can conclude that S of F1 of t is equal to S of F2 of t, which tells you that F1 of t is equal to H times F2 of t for some homographic H. Okay, so this is this property that we use to conclude that actually these two equations, there's no definable correspondence between them, but to make sense of this intersection of an algebraic variety with this object, we work in this kind of object. I mean, they work in this kind of object. Okay, so I will stop here.
Questions?
This is a kind of a question. I mean, the strongly minimal condition. So, I mean, I guess we have. Do you expect I guess this must be some sort of special condition, but I mean, do you have other examples of foliation? I mean, I guess I'm just wondering, like, what's the geometric meaning of it?
So the first thing is that you cannot, so here this notion depends on the vector field you pick tangent to the foliation. So here we have this foliation, which is H delta, okay, on P. Okay, and we have these two projections. Okay, and so if you lift the vector field d over dz to this foliation, the fibers will be strongly minimal. This is the case H equal to 0. But if you lift the vector field d over dy tangent to this foliation, okay, then this is a G principal bundle and this is not strongly minimal at all. So the first remark is that it depends on the vector field you take tangent to the foliation. The second thing is that, so something that is true is that if you take generic, very, like we define very generic foliation, very generic vector field on the plane, okay, then the solution will be strongly minimal. So this is not such, it's not like, it tells you that there's no way to decompose your differential equation. Okay, and so if you take something that is very generic, you expect it to be strongly minimal. And here, this is something that is far away from being very generic, but this is still strongly minimal.
Yes, T1 is not orthogonal to T2. It should be different there because of the statement.
Here?
Yeah, because they are not orthogonal. It should be different.
No. So if they are different, then they are orthogonal. So if they are non-orthogonal, then they are equal. Okay, so being, that's also something funny about this kind of statements is that we define the negative version, right, to be non-orthogonal. And then we say if A different to B, then they are orthogonal. There's no, so being orthogonal means there's no definable correspondence. Okay, so the positive condition is defined by a negative condition. Okay, so this is confusing.
Any more questions? Okay, now let's thank Remi again. I guess double thanks from us organizers for you. Doing 4 lectures with very little notice. And okay, so this afternoon we resume with the problems and discussions around 1:30, and then there will be a talk at 4:30.
Great talk. Really nice. Thank you. So I have a bunch more naive questions. So, okay.